we're going to look at the topic of apparent weight. It's a little bit tricky, not super tough, but also not the simplest thing ever. So, apparent weight. So the first thing that we need to remind ourselves of is what weight is to begin with. Okay. So when we take a mass, we put that mass into a gravitational field, like say the gravitational field of the Earth, right? So we're near the surface. We've got this force field that acts on mass. Well, this mass will feel a force. And we measure the field strength here in terms of how many newtons every kilogram of mass experiences near the surface of Earth. And that works out to be 9.81. You get 9.81 newtons per kilogram at the surface of Earth, right? This value comes from this idea of force is equal to mass times acceleration. Okay? Now, we also learned that this unit is the equivalent unit of meters per second squared. And the reason why is because the Newton is a kilogram meter per second squared, and we're multiplying it by kilograms. Those cancel out, and there you are. Okay? So the concept of weight then is, let's use a person as an example. So they're a mass, right? This person has a mass. Let's say their mass is, we'll make them 100 kilos. They're a big person. Okay, so 100 kilogram person. And weight is the amount of force they would experience due to the acceleration due to gravity, due to Earth's gravitational field working on them, right? So weight is equal to mg, okay? You might also see it written like this, Fg is equal to mg, okay? These are interchangeable ways of thinking about this, okay? So for this person, they're 100 kilograms, they're in a force field that's 9.81 meters per second squared. So they would feel a weight, or they would have a weight, I should say, of 981 newtons. That is weight. This is mass. In everyday speech, we often interchange weight with mass. Say, you have a weight of 89 kilograms. Oftentimes we'll say pounds. But really, when we're talking kilograms, we mean mass. This is weight. It's when the field is acting on the person. So far, so good? Now, when we're talking in everyday life about weight, I have a weight of this or I have a weight of that, actually what we're talking about is something called apparent weight. Apparent weight. So let's think about this person, right? Or a similar person. We'll draw another picture to talk about this. So here's the surface of Earth. Here's some object sitting on the surface of Earth. A nice square box. We know that there is force of gravity acting on here, which we call weight. And we also know that the ground pushes upward on the object to, not allow this object to accelerate through the ground. We call that the normal force. If an object is sitting still on the surface of Earth, the net force on them is equal to 0. Okay? Weight is always directed towards the center of the Earth. But what this object would experience as its weight, or if we change to a person, and imagine that we're putting a scale underneath them, right? So here's a scale. The underside of a scale has a spring on it, right? So the weight of the person pushes down on the spring, right? But the spring pushes back up on the person. So if you step onto a spring like this, or like the springs inside your scale, they sink down. They're connected to a little readout. They sink down, and you end up with this balance where the spring and the weight become equal to one another. Does that make sense? Now, what we're actually reading on the scale is this part of things. We're reading how hard the scale has to push up on you to prevent you from accelerating down. That's what a scale is reading. You are feeling your weight in your feet, right? Due to the fact that Newton's third law, there's a reactive normal force pushing up on the bottoms of your feet whenever you walk around. If you gain weight, if your weight gets larger, okay? So if you pack on some mass, your weight will get larger. This will sink down lower because it will have to push up on you harder, okay? We will say that you have a larger apparent weight, okay? So that's kind of like the basis of this. Then something interesting might happen. First of all, what happens if you and your scale jump off the side of a cliff and you're falling down? What would your scale read in that scenario? What do you think it would read? Would it read your weight? If you and the scale are both falling? Probably not, right? The scale would sort of like hover away from you and it would read 0. In that scenario, you have 0 apparent weight. Do you still have weight? You do still have weight, because remember, we define weight as just mg. That has not changed. But you feel weightless because there's no more normal force to push up on you. You've jumped off of something and you're falling. Okay? If an astronaut takes a scale into space, can they stand on it? No, they would just float around and the scale would read nothing, right? Their weight has not changed because there's still a gravitational pull on them, but they've got themselves into a situation where they are apparently weightless. Okay? So you can be weightless and still be in a gravitational field. Okay? So we're going to examine how that might work. All right? Because, I mean, if you're falling, you obviously have not left Earth's gravitational pull. It's pulling you towards it, right? You're not drifting off into nowhere. So how does that work? Well, this is what we're going to say. We're going to say, imagine, we're going to keep this a little bit simpler. We're not going to say you jumped off a cliff, but let's say you got into an elevator. Oh man, that's a terrible drawing. Let me just fix that. Let's say you got yourself into an elevator. Okay, let's draw an elevator. There. That's what an elevator looks like. The perfect square. And let's say you put your little scale. Here, we'll do like the kind of scale that's downstairs. Okay, one of these like stand-up scales, right? So there it is. There's the readout on the scale. And there you go. Okay. Let's say at first the elevator is sitting still. Okay. Well, in order to get going, the elevator has to accelerate either down or up. When the elevator starts to accelerate upwards, well, what's happening, if this is considered to be the mass, what's happening is the normal force must get larger than the gravitational force. Okay? So let's just think about that. When you're sitting on this surface, right, you got your weight down, you got your normal force exactly equal to your weight. Nothing can happen at this point. Okay? This is when you walk onto the elevator and you're sitting still. But now the elevator has to accelerate you upwards. What has to happen to the normal force under your feet to make you start accelerating? You must have a net force, right? In that case, the normal must get larger than Fg, right? We have to have a positive net force, a net force that accelerates you upward. So for a little while, for a time, and you can feel this when an elevator starts to do it, the normal force grows and it becomes larger than Fg. The scale has to push harder up on you to accelerate you. What would happen to the readout over here? Would it get higher or lower? Higher. While the elevator is accelerating upward, your apparent weight gets higher. Okay? Once the acceleration stops, now you're moving constantly, right? Now you're moving constantly. So these forces must have gone back to a net force of 0. So this drops back to its regular weight. If you're either traveling constantly or sitting still, your apparent weight and the weight that you would, actually weigh would be the same. So your weight down and your apparent weight would be the same. So you have to think of apparent weight as an upward force. Okay? Now let's go the other way. Let's say we're accelerating down. Okay? So let's put this is for up. from rest. Up from rest. We're gonna look at a couple of other scenarios too in a second here. Now let's imagine we're going down from rest. To go down from rest, can we increase the downward force on our body in an elevator? We can? What's providing the downward force in an elevator? What's accelerating us downward if the elevator starts to move down? Do they have motors that have to push the elevator down? Yeah, you just let gravity do it, right? You just let gravity do the work. So, for an elevator to go down, essentially, it slowly reduces the normal force, right? So it has to accelerate downward. So the normal force shrinks, okay? So during the elevator accelerating in the downward plane, the normal upward force becomes less than gravity, the gravitational force. And I'm just talking about magnitudes here. Don't worry about direction. I'm just talking magnitudes, okay? This is accelerating down from rest. So in that case, if the normal force is less than Fg, what does this scale read? Well, it's pushing up on you less than it was when you were sitting still, right? Because your F net has to be, here your F net had to be up, here your F net has to be down. So what is this going to read while you're accelerating downward? Well, it's going to read lower. So as this starts to drop, your apparent weight decreases. Okay, so there's two other situations that we need to talk about with this elevator business. So let's just imagine here, here's your scale, here's your person, okay? And let's say the whole elevator is traveling downward at a constant velocity. If it's got a constant velocity, that means that there's zero acceleration on this person, and that must mean that their weight and their normal force is equal. However, if they're getting to the bottom floor, they need to slow down. At that point, the normal force must increase, right, to accelerate them positively and therefore slow their negative travel down. While that's happening, okay, the springs on here must be pushing up harder, and you're going to have a larger apparent weight. So in other words, okay, during this, okay, the normal force is larger than the weight. Okay, and the last one is if the elevator is moving up but slowing down. Let's draw this scale. So it's moving up, but it's slowing down. Okay. Oh, my drawings are getting awful. It's a scale, not a toilet. Okay, so you're traveling up. These guys are equal to each other, but this person needs to slow down because you're reaching the floor. The way to do that is to decrease the normal force. So the springs have to push up on you less, and your normal force ends up to be less than your weight. Okay, so it decreases. It gets smaller. Your apparent weight would therefore decrease. Okay? Now what would happen in an elevator if you went from rest to falling? If the cable snaps and the elevator goes into free fall, what happens to apparent weight? What happens to the normal force? It goes to what value? It goes to zero. In that case, we might say you're weightless. You're not really weightless because gravity's still pulling on you, but your apparent weight has gone to zero. Okay? So let's math this thing. Let's math it. So just to clarify, your actual weight, that can't change. That's found as mg. Your apparent weight can, because your apparent weight is based on how you feel you weigh. In other words, what the normal force is doing to you. You can't feel your real weight. You can only feel your body's reaction to your real weight and the floor's reaction to your real weight. You can only feel like you have weight if the floor is pushing back up on you. It's kind of like flipping your concept on its ear, maybe. I'm not sure. This is not a natural way to think about it, I don't think. What I really mean is the force pushing up on me when I'm talking about my weight, but if I get heavier, I fall, I push down harder on my feet. You see what I'm saying? It's a little bit tough. Conceptually, it can be tough. It can fool people. So, let's talk about this. So if we measured the net force on this person, the net force, I guess, is going to be made up of the normal force plus the gravitational force. This, of course, is going to be a negative value, right? It'll be a negative value because these forces aim in opposite directions. So we could kind of like rewrite this as Fn plus negative Fg, or then even rewrite it like this. The net force is equal to Fn minus Fg. Things. Okay, so the net force on an object, right, if we look at it, is just going to be whatever mass that object is times its acceleration. Okay, so if we look at a person in an elevator, right, the net force on them is going to be considered when we look at what is Fg, you know, what is Fn, is it smaller, is it larger, okay, and then we're going to see how this person is accelerating, right, and that's going to be the net force that's left on them, right? So net force is just their mass times whatever acceleration they have. In this case, they're accelerating downward, right? If Fn is larger, they're accelerating upwards. So F net is just the difference between these two forces. Does that make sense? And it's going to be equal to ma. Okay, and then the weight, or Fg, is going to be equal to mg. So we have this information, right? We could say the elevator, and therefore the person in it, accelerates upward at 2 meters per second squared, or it accelerates downward at negative 2 meters per second squared. We have that information, right, based on what the elevator is doing. And we have mg, assuming we have their mass. So if we want to know what apparent weight is, we really have to solve for what Fn would be, right? So what we can say here, if this is F net, we could say that ma equals Fn, which again is going to be apparent weight, minus mg, or that Fn is equal to ma plus mg. Okay? Now the interesting thing is, this value is either going to be up or it's going to be down. So it's going to be negative or positive, right? So we're just going to rewrite this formula. We're going to pull m out of here, right? So what you end up with then is you end up with this, equals m g plus a, or m g minus a. If we're just talking magnitudes now, right? We're just going to be talking magnitudes. I find that that's easier than trying to mess around with negatives and positives. I think it makes more sense to use your common sense on whether you're going to have a larger or a smaller value and work backwards from that. I think it causes less confusion. Okay, so this is g, we know what that is, and a is the acceleration of the elevator. If it's accelerating up, or if it's a situation where you have a larger Fg, it's going to be plus. If it's a situation where you have a lower apparent weight, it's going to be a subtract. Okay? So let's just write a final scenario out here. What we can say here is we can say that your apparent weight which we can just call, I guess, WA, will be equal to mg plus or mg minus a. Okay? Let's do two examples. An elevator accelerates up from rest at 2 meters per second squared. Find the apparent weight of a 100 kilogram passenger. So the first thing I want to note here is that the person's real weight, mg, will be 981 newtons. Okay? If the elevator is accelerating up for rest, from rest, that must mean we have a case where the apparent weight, aka the normal force, is larger than Fg. will their weight be greater or less than, or will their apparent weight be greater than or less than their real weight in this scenario? Greater. It will be greater. And let's solve for that. So this is a G plus A scenario. So what we end up with then, mass is 100 kgs. Shouldn't write in this red, I don't like it. 9.81. And again, remember, we're dealing with magnitudes to keep it simplified. Don't put a negative in here, okay? Just use the magnitude. Plus 2.0 meters per second squared. So what we should have here is 100 kgs times 11.81 meters per second squared, or 1181 newtons. So the person's weight, apparent weight, has increased. Okay? Now, the elevator reaches the 4th floor and slows. Okay, so it's traveling up, right? So it's the same scenario. Travels up and slows at 2 meters per second squared. Find apparent weight while slowing down. And, you know, once it's reached its traveling speed, the person's apparent weight becomes the same as their real weight, okay? Because they're traveling at a constant velocity. So traveling at a constant velocity doesn't do anything. So find apparent weight while slowing. So it's the exact same concept, except now you know that it's subtracting G minus 8. So we've got 100 kilograms. We've got 9.81 minus 2 meters per second squared. So you've got 100 kgs times 7.81 meters per second squared, and they weigh 781 newtons while slowing down. Their mass did not change, but how they feel like they weigh did change.